In this video, we will do an example where we maximize a multivariable profit function where we're given two demand equations. So I'm going to look at this example. It's a bit long, and that's why my screen is zoomed out so I can see the whole thing. But we're getting more and more used to these longer word problems, so let's see if we can read it and break it down. So the question says, you sell furniture. You found that demand for sofas and giant beanbag chairs depends partly on the price of the other. They're known as companion goods. Let P1 be the price in hundreds of dollars of a sofa and X be the number of sofas sold. Let P2 be the price in hundreds of dollars of a beanbag chair and Y be the number of beanbag chairs sold. Okay. The demand equations are, and then we have these two equations, one for what P1 is, remember P1 is the price of a sofa, and one for what P2 is, and P2 was the price of a beanbag chair. Suppose sofas cost $400 to produce, and beanbag chairs cost $200 to produce. Fixed costs are $30,000 per month. Find the number of sofas and beanbag chairs you need to sell in a month to maximize profit. Alrighty, so a lot of information here, but let's see if we can start to break this down into the parts that we need. So the first thing we need to identify is what is it that it wants us to maximize or minimize? And the question says it wants us to maximize the profit. So at some point we're going to need to write the profit. So recall that profit equals revenue minus cost. And recall that revenue is price times quantity. And in this problem, we actually have enough information to write the cost function down right now, at least I think. But you know what, maybe let me actually hold off on that. Let's do revenue first. Okay, so if I do revenue, I'm going to need to multiply the price with the quantity. But there's two items that we're talking about here, sofas and beanbag chairs. So I'm going to need to know the price of a sofa times the quantity of sofas that are sold. The quantity of sofas. And then add that to the price of a beanbag chair times the quantity of beanbags. All right, so let's plug in for these first. Okay, I'm going to zoom in a little bit so it's easier to write. Okay, so the price of a sofa was P1. So let's plug that in. So our revenue is going to be equal to P1, which is 46 minus 3x plus 2i, times the quantity of sofas. That was x, plus the price of a beanbag. The price of a beanbag was P2. So plus 72 plus 3x minus 5y, times the quantity of beanbags, which was y. Okay, so that's revenue, and I could simplify this a little bit by distributing x and distributing y, and that gives us 46x minus 3x squared plus 2yx, and then distributing the y, we'll get plus 72y plus 3xy minus 5y squared. Okay, so we have our revenue. We would now need to do something similar for the cost. Okay. All right, so for the cost, we got to factor in the cost of sofas, the cost of beanbag chairs, and the fixed costs. But remember that our costs are going to be in hundreds, because that's what the question, does it say that at some point? Yeah, it says the prices were in hundreds of dollars, so let's stay consistent with those units. Okay, so first let's do cost of sofas. Well, it's $400 for each, so if I write that in hundreds, that would be 4 and then times the quantity of sofas, which is X. And then plus, I got to do the same thing for beanbag chairs. They're $200 each, so in hundreds, that's 2. And then times the quantity, which was Y. But then we also got to factor in the fixed costs. Fixed costs were $30,000 per month. So in hundreds, if I divide this by 100, we'd get 300. So recall that the fixed costs are the costs when the quantities of the items that have been sold are 0. Sorry, another way to say that is the fixed costs are the costs that we have even when we've sold no items. So when X and Y are both equal to 0, the cost, C, must be 300, which is 30,000. But if in terms of my units, I would need to write the number 300. So that's good. If I were to plug 0 in for the X and 0 in for the Y, I am getting that C is equal to 300. That's matching up with what the fixed cost should be. Alrighty, so we have the revenue, we have the cost. We are now ready to write down the profit. Alrighty, so here was our revenue one more time. I could simplify this because I have these two like terms, 2yx and 3xy. So we get that revenue is equal to 46x minus 3x squared plus 5yx, combining those terms, plus 72y minus 5y squared. So now we could write our profit. Profit is revenue minus cost. So revenue is 46x minus 3x squared plus 5yx plus 72y minus 5y squared minus our cost. I got to put that into parentheses, so I remember to distribute my negative sign. Our cost was 4x plus 2y plus 300. And now if I do distribute the negative sign, we'll get 46x minus 4x, which is 42x minus 3x squared plus 5yx. We'll get 72y minus 2y, which is plus 70y, and then minus 5y squared, and then minus the 300. Alrighty, so that is our profit. We now want to find the critical points. So at this point, we've done all the setup. We have set up our profit function. It's just a matter of finding where that max happens. And this I want to leave for you to try. So I want you to pause the video for about 5 minutes. These optimization questions, maximizing, minimizing questions are a little bit longer, which is why I'm giving you a little bit more time. But really try this. 4, 3, 2, 1. Pause that video. Pause that video. This is a really good check-in to see how well you understand this process of finding critical points using that second derivative test, so we can determine, do we have a max or do we have a min here? All right, so hopefully you've done that. Hopefully you paused it for about 5 minutes. If not, really encourage you to do that now. That is super important. All right, so I'm going to trust that you've done that. Let's find those critical points. So let's set our partials, px equal to 0 and py equal to 0. So if I take those partials, let's take the partial with respect to x. So for the first term, that derivative is 42. For the next term, it's minus 6x. The next term would be plus 5y. And then all the remaining terms would be 0 because they don't have any x's in them. And that equals 0. So notice that I'm picking up the speed a little bit now with my partial derivatives because we've done a few examples. But again, if this is going a little bit too fast with the partial derivatives, I would definitely encourage you to pause the video and really make sure you understand how I got each of these terms. And if you still have a question, then definitely come and use our resources for help to ask about them. So now the partial with respect to y. For the first term, that would be 0. And for the next term, because neither one has a y in it, for the third term, we'd get 5x. For the next term, we'd get 70, in fact, let me rearrange the order. Let me write the 5x underneath the minus 6x, and the 70 I'll put it in front, just so I can line up similar terms directly underneath each other. Okay, for minus 5y squared, that partial would be minus 10y. And then last term would be 0, because that's a constant. So we have this equals 0. So we have equation 1 and equation 2 in this system of linear equations. So just like in our last example, we can use elimination to solve this. I am going to take my first equation, and I notice that if I multiply by 2, the 5y will become 10y, and that will cancel really nicely with the minus 10y from the second equation. So I'm going to take equation 1 and multiply by 2, so that'll give us 84 minus 12x plus 10y equals 0 times 2 is 0. Second equation, we keep it as is. 70 plus 5x minus 10y equals 0. So that now we can add our equations together. So 84 plus 70 is 154. Let's write it in black. 154 minus 12x plus 5x minus 7x. The 10y's are going to cancel. One's positive, one's negative, so when I add, they cancel. And this equals 0 plus 0, which is 0. So moving minus 7x to the right, we get 154 equals 7x. And dividing by 7, we get x equals 154 over 7, which is 22. All right, so now we can take that and plug it into either equation. Plug x equals 22 into either equation to find y. So I'm going to go ahead and plug it into the second equation, just because then I get to multiply it by 5, which is a slightly smaller number than negative 6 if I were to plug it into the top equation. So I get 70 plus 5 times 22 minus 10y equals 0. Whoops, not 10, equals 0. So we get 70 plus 5 times 22 is 110 minus 10y equals 0. 70 plus 110 is 180. Let's move negative 10y to the right. So this will equal positive 10y. And now I can divide both sides by 10. That gives me y equals 180 over 10. And dividing, I get 18. So nice, we have our value of x and our value of y. So we can write down our critical points. We just have one critical point. X is 22, y is 18. So we are ready to find h, our Hessian. So we can test whether this critical point gives us a max or gives us a min or gives us a saddle point. We're hoping it won't be a saddle point because this question was asking us to maximize profit. So we're really hoping it's going to be a max. Okay, so let's recall our partials. The partial with respect to x was 42 minus 6x plus 5y. And the partial with respect to y was 70 plus 5x minus 10y. All right, so recall our formula for h is pxx times pyy minus pxy squared. So let's take these partials. If I look at px and I take the partial one more time with respect to x, we're going to get minus 6. If I look at pyy and I do the partial one more time with respect to y, we're going to get minus 10 or negative 10. And then minus pxy, if I look at px and I do the partial with respect to y, we'll get 5. And by Clairaut's theorem, even if I had looked at py first and then done the partial of that with respect to x, I would expect to get the same thing. And if I did that, if I looked at py and I did the partial with respect to x, I do get 5, which is good. All right, and now simplifying, this is 60 minus 25, which is 35. Okay, so what we care about the most is that is a positive number. So I'm going to make my table of critical points, the value of h, the value of pxx, and the conclusion. So our critical points, we said 1, it was 22, 18. And the value of h was 35, and the key thing we care about there is, well, that is a positive value. And when h is positive, we need to know the value of pxx. And if it's positive or if it's negative, and pxx, we got -6 for it. Okay, so when h is positive, but pxx is negative, the conclusion is that we have a max. All right, so what was the question asking us? It wanted us to find the number of sofas and beanbag chairs we need to sell in a month to maximize the profit. So the number of sofas and beanbag chairs were x and y. So it's asking us for those values. Those were 22 and 18. So let's write our conclusion with a sentence. We maximize our monthly profit by selling. X was number of sofas, so 22 sofas, and Y was the number of beanbag chairs, 18 beanbag chairs. So this question did not ask us what that max profit was. It just asked, well, what are the values of X and Y? How many sofas and beanbag chairs did we need to sell to give us that max? If it did also ask us for that maximum profit, then we'd have to plug in our values of X and Y that we got, the X and Y values, into our profit function, which would have been up here. We would have plugged it into our profit function if it wanted us to also find that maximum profit. So in terms of our goals for this section now, we have finished our last goal, which is doing more second derivative test examples that apply to scenarios involving like profit, cost, revenue, and demand.